So I'm thinking I should get a better camera, so I have to draw some of these out ahead of time. But look at problem number 10 here. We're looking at 40 teams, and we find that the percent of them that are profitable, NCAA athletic programs that are profitable are 55% or a sample portion of 0.55. So we want to build a 95% confidence interval for that true proportion. So we look at our formula sheet. Here's our three confidence interval equations. We're looking at an example where we've got a sample proportion. So if nothing else, match up the notation here of p hat, we have a sample proportion. So we're going to plug in that sample proportion of 0.55, where everywhere we've got that p hat. Our sample size was 40. The only thing left we really need to do is look up that z-value. So we wanted the 95% confidence interval. So our alpha was 0.05, right? The kind of percent outside our interval in decimal form. So that means half of alpha over 2 would be 0.025 on each side of our confidence interval. So I want the z-value that gives me 0.025 on each side. So I go to a standard normal table. So we're working in reverse or the inverse here because I have the area. So I'm going to find the probability I want in the middle of the table. Here it is, 0.025. I go over negative 1.96 was the column it was in, right? So we go down to that 0.025, negative 1.9, we went up to that 0.06. So negative 1.96, it would be the z-value that gives that to us. Now, we said we kind of can ignore the negative sign because our confidence interval equation, right? We're building it around that 0.55. We're adding this positive z-value to get our upper bound. We're subtracting it to get our lower bound. And from here, it's just a matter of plugging everything else into that equation once we identified it. And now we're done, right? So I said one helpful hint is maybe calculate this ahead of time. So you're just plugging in one number there. Recall this represented the standard deviation of our sample proportions. So we go here. Calculate this real quick since I don't have the answer key pulled up. So let me get my calculator out. So 0.55 plus 1.96 times the square root of 0.55, 40. So I believe 0.704 is that upper bound. So D will be the right answer. For the sake of time on the exams, notice like most of the time, if you find the correct upper bound, I mean, you right away can identify what the confidence interval is, so you don't have to waste your time calculating the lower bound. So let's say we've got the exact same data, but now we've got this report that the NCAA, Forbes says that 45% of programs are profitable. We want to test for whether or not that true population proportion is different from this reported amount. So we want to test for whether or not it's different than this reported amount. So what you want to test for is your alternative hypothesis. So we'll kind of write out, I want to know, is it not equal to 0.45, right? So not equal to 0.45. We assume the opposite is true, or the null hypothesis over here is that it's exactly equal to 0.45, okay? So the next question is, what's the value of the test statistic, right? So we've got a two-tailed test, right? And now we're going to try to come up with the value of the test statistics. So I go to my formula sheet. I'm kind of reminded I've got three different equations for that test statistic. So I've got a sample proportion. So I'm going to be using this one right here. My sample proportion was 0.55. That assumed true proportion was the 0.45 we just put into our null alternative hypothesis. And the sample size was, I can't remember. The sample size was, let's say 40, but that doesn't sound right. Oh yeah, 40 teams, right? So we've got everything we need. It's just a matter of plugging in our values there. Now, one thing to kind of help from making some easy mistakes potentially is we're thinking about if what we assume to be true is in fact true, and that population proportion is 0.55, we saw a sample proportion of 0.55. So what we're trying to do is convert this value into a z-value or a z-statistic here, since we're doing a hypothesis test. Well, if I see something that's above my assumed true value, I know that that test statistic is going to be positive, right? It's going to be a certain number of standard deviations above the mean. So right away, I should be able to rule out D. From there, it's just a matter of plugging in those values into our calculator. So I'll kind of write it out here just so we can see it. All right. Well, we took the sample proportion we found minus the assumed true proportion divided by the assumed true proportion times 1 minus the assumed true proportion over that sample size of 40. If I do that, I should get negative approximately, not negative, sorry, positive 1.27. Okay. So I don't even know if the next question asks for p-values. I don't think it does, but if I did, we would find the p-value in the following way. Actually, we got a p-value down here. So I'll wait and hold off on that one because I want to mention something on 14. So the next thing is, what are our critical values? Well, first of all, if we have, if we've got a two-tailed test, it's almost like we're thinking about a confidence interval because we've got half of alpha in each tail. So all our critical values are going to be, right, are the z values that give us that desired alpha over 2 in the tail. So we're really going to be looking up what? An alpha of 0.1, 0.05, and 0.01. For a two-tailed test, we're dividing those all by 2. So, right, alpha over 2 is 0.05, 0.025, and 0.005. Said, kind of probably the easiest way to do that, if that's the area that we want in the tail, if I go to my student t table, even though I know for a proportion I should be using the standard normal table, I can go to that last row, and that last row gives me my standard normal values, right? So it's kind of a little bit of a cheat code that we had using the student t. The last row gives us our standard normal values. So we wanted 0.005, 0.025, and 0.05 in our tail. So we go down here, 1.645, 1.96, and 2.576. However, we have to remember that we've got pairs of critical values. So I think these kind of, I rounded this one to the second decimal, right? But these were our 3 kind of critical values. And we know that every single level will have a pair, so plus, positive, and minus. So here, you've got a two-tailed test, you automatically have ruled out B and D. You know you have to have pairs of critical values. You then have to remember, oh yeah, that means that there's alpha over 2 in each tail now, because alpha is the total area in the tails, and we can find those 3 critical values. So a lot of times on the exam, if you would have gotten 12 wrong, if I asked you to find the p-value, you would have gotten that wrong as well, right? Because you need the test statistic to find the p-value. And so I'll give you an assumed true test statistic of 1.34. So you have this assumed true test statistic of 1.34, and you want to find the p-value, make your rejection decision. So instead of this 1.27, I gave you an assumed true test statistic of 1.34. Now, don't read into these at all. This one happened to be pretty close to what the other one was, but it doesn't necessarily have to be the case. Sometimes I'll even give you an assumed true test statistic with a different sign than what the real one was. So we go back and recall, we had a two-tailed test. So I can use this test statistic, and I can look for what's the probability I saw a sample proportion this high from that assumed true value or anything even higher. But remember, that only represents half my p-value, because it would have been equally as likely for me to see something on the other side of the distribution that went against the null for a two-tailed test. So I can look up that 1.34. The table will tell me the area to the left, right? So if we go ahead and do that, and I look up, and remember, it's a proportion example, so it should be a standard normal distribution. So 1.34, so 0.9009. So this is 0.90, actually, was it 009 or 090? I think I read it wrong. 0.9099. Okay, I did say it wrong. Okay, so 0.9099. So 1 minus that, it's going to be what? 0.9, no, not 0.9, 0.099. 0.901. So that's the area in this tail. It's a two-tailed test, so I have to make sure that I then multiply it by 2, and I get 0.1802. So go back, then identified our p-value was 0.802. Do I fail to reject at an alpha of 0.1? Well, I only reject if alpha is less than, if my p-value is less than alpha. So if my p-value is less than alpha, I reject. 0.18 is not less than 0.1, so I fail to reject. Okay. So those are the next set of problems.